Hello, I'm Natalie Rhea. Today I'll be discussing Lab 4, a macroscopic view of DC and RC circuits for Physics 2212. The objectives of this lab included predicting the behavior of circuits containing resistors in series, using PHYS circuit construction kit to build simulated circuits, measuring the actual values of conventional currents and potential differences in the simulated circuits, and examining the behavior of ohmic resistors and capacitors. The important fundamental principles at play in this lab included the loop rule, which states that the sum of voltages in any closed loop in a circuit is zero, Kirchhoff's node rule, which states that at any junction point in the circuit, the sum of the circuits entering the node must be equivalent to the sum of the current exiting the node, and Ohm's law, which states that the electric current in a circuit is proportional to voltage and inversely proportional to resistance. Now onto the first circuit modeled, which consisted of two 1.5 volt batteries, two resistors, one 45 ohms and one 100 ohms, and two ammeters. I used Ohm's law to predict that the readings of both ammeters should be about 0.0204 amps, calculated by dividing the total voltage in the circuit, 3 volts from the two batteries, by 147 ohms from the two resistors. I then constructed the circuit using the simulator. As you can see in the left picture, the ammeters show that the currents are the same in both locations in the circuit. As predicted, the current in both locations in the circuit is 0.02 amps. When one of the ammeters was flipped, shown in the right photo, the current reading was the same. Next, one of the ammeters was removed and replaced with a voltmeter. The circuit loop is then broken, as the voltmeter does not carry current across it, so the ammeter reading is 0 amps. When placed across the break in the circuit, the voltage reading is -3 volts, equal in magnitude to that provided by the batteries, 3 volts. The reading is negative because the red probe is touching a wire at lower electric potential than the black probe. Next, the break in the circuit was closed with a wire, and the voltage was measured at different locations in the circuit, as shown in the series of photos. The predicted round-trip value for the potential difference is 0 due to the loop rule. Once the voltages of our circuit were measured, their sum was indeed found to be 0 volts, as seen in the calculations on the right. This graph displays the electric potential at different positions around the circuit. Moving from left to right across the graph, the electric potential increases to 3 volts due to the two batteries, stays at 0 while in the wires, and then decreases when it passes through each of the resistors, making a total potential difference of 0 volts. When in use on the circuit, the virtual voltmeter does not alter the current at all because the voltmeter has infinite resistance, so no current from the circuit travels through it. This is not very realistic. A real voltmeter cannot have infinite resistance, so it would alter the current in the circuit slightly. The voltmeter was then replaced with the ammeter in parallel with the 100 ohm resistor. Now the 100 ohm resistor no longer contributes to the circuit, and the current has increased from before. It was previously 0.02 amps, now it's 0.06 amps. This is because the current can travel through the ammeter instead of going through the resistor, and the path of no resistance is preferred over the path with 100 ohms of resistance. I then used Ohm's law to calculate the resistance in the two resistors, the wire, and the ammeter, using the voltmeter and ammeter readings collected earlier in the lab. The resistance in the two resistors was close to their predicted magnitudes, 47.95 ohms and 102.05 ohms. The resistance in the wire and in the ammeter in this ideal simulation is 0. The next circuit constructed was an RC circuit, or a circuit that contains both a resistor and a capacitor. First, a circuit consisting of a 9-volt battery, a 10-ohm bulb, and a 200 millifarad capacitor is constructed. When the battery is first placed into the circuit, the light bulb starts off bright but gets dimmer and eventually turns off. This is because charge flows and slows down until stopping when the capacitor is fully charged. Before it stops, the current moves counterclockwise in the circuit. The capacitor starts off uncharged but eventually becomes charged with a potential difference equal in magnitude to that of the battery. Next, the battery was removed from the circuit. When the battery is removed, the light bulb starts bright, but gets dimmer and eventually turns off, same as what occurred while the capacitor was charging. Now the current is moving clockwise in the circuit. The capacitor starts off fully charged, but as the charge stored on the capacitor flows through the light bulb, the capacitor eventually becomes fully discharged, and the current stops. Next, I measured the time it took in seconds for the capacitor to charge and discharge using the 10-ohm bulb and then the 20-ohm bulb. It took longer for the 20-ohm bulb to both charge and discharge. For both light bulbs, it took a bit less time for the capacitors to discharge than to charge. Next, I set up a circuit in the simulator with a 9-volt battery, a charged 200 millifarad capacitor, and a 30-ohm light bulb. I used the voltmeter to measure the voltage across the capacitor and set the capacitor discharging and recorded the voltage across the capacitor approximately every second for about 20 seconds. I then plotted this data on a graph with the y-axis showing the natural log of voltage divided by initial voltage, and the x-axis displaying time. I was then able to use the slope of the trend line of this data to calculate the RC of the circuit. RC is the time constant of the circuit, the time at which the voltage difference has dropped to 1 over e of its original value. Because the slope of the graph is equal to -1 over RC, and the slope was 0.176, I found RC to be 5.68 seconds. Discussion question 1. In our simulation, the ideal ammeter provides zero resistance to the circuit, but if doing this lab in real life, a real ammeter would provide a small amount of resistance, lowering the current traveling through the real circuit. Discussion question 2. In our ideal simulation, if we had just a circuit with a battery and a capacitor, the capacitor would be charged immediately. However, if we made the same circuit in real life, the capacitor would take a short while to become fully charged. This is because all components in the real-life system, including the wires, provide a small amount of resistance. That's all for this lab. Thanks for watching.